Okay, today we're going to talk about relative or local minimum and maximum points, which we often call in general extrema. And these are just the highest and the lowest points on the graph in a certain neighborhood. So there's a relative max, here's a relative min, here's a local max, here's a local min. In this neighborhood, a relative high point, a relative low point. Okay? We define relative extrema on an open interval. And what I mean by that is if I were to randomly choose a particular neighborhood, let's say right there, and I was going to look for the local minimum, I'm looking for the place where the smallest y value is. Well, that's obviously right here, okay? So intuitively, I think we all see that, yeah, sure, that's a relative minimum, okay? There would be no relative maximum because we would not count this point because relative minimums and maximums are defined on an open interval. So this point wouldn't be counted, okay? And the point really, really close to that would be just that, very, very close, but wouldn't be an exact point. So on this interval where my rectangle is, there would be no relative max, there would just be a relative min, okay? But intuitively, you just need to think of it as in a certain neighborhood of the graph, excluding the points on the end, so within some open interval, it's the highest or lowest point on the graph. Now if you take a look at this, what do all of these points have in common? Well, relative mins and maxes all occur at locations where the derivative is either 0, or, now I've got a cusp here, or where the derivative is undefined. Okay, that's going to be a really important point in terms of how we determine where our extrema are. They occur where the derivative is 0 or undefined. Okay. However, you'll notice that we've also got a point right here where the derivative is 0, but this point is not a relative minimum or maximum. So it's not enough just to say that relative mins and maxes occur when the derivative is 0 or undefined. We have to look a little bit further. Alright, so I've outlined here the definitions of relative min and relative max as I've just explained. We use the term relative extrema when referring to either a relative min or a relative max. And theorem, just to summarize, is that if a function has a relative extrema, minimum or maximum at x equals a, then it will occur at a location where the derivative is 0 or undefined, which, remember, is a critical point. In other words, all relative maximums and minimums must occur at a critical point. However, not all critical points are locations of where relative extrema will occur, such as this point right here. Okay, derivative is 0, but there is no relative extrema. So the natural follow-up question is, okay, so you're telling me that relative mins and maxes occur at critical points, but how do I decide whether a critical point is a relative min or max? Okay, so this is our central question. Alright, so we have two basic ways of determining this. You'll remember when we were looking at how we decide if a function is increasing or decreasing, we determine that by looking at the sign of the first derivative. Okay, so I've got a situation set up here. I've got three critical points. Okay, again, places where the derivative is 0 or undefined. And I know that on either side of my critical points, I have the derivative being negative or positive. Okay, now you'll remember that when the derivative is negative, the original graph is decreasing. And when the derivative is positive, the original graph is increasing. Okay? And in these two sections, they're both negative. Well, if you think about it, if a graph is decreasing and then it's increasing, there must have been, right here, a low point. This would be the location of a relative minimum. If the graph is going up and then going down, this must be the location of a relative maximum. We have the graph going down here, and then we have the graph continuing to go down, even though there was a critical point. So the derivative might have been 0 there, for example. Okay. Well, at this critical point, there is neither a relative max or a relative min. Okay. So this is one major way of determining whether a critical point is a relative min or max, and we call this the first derivative test. And it says that if the first derivative changes from positive to negative, as it did right here, then we're talking about our critical point being a relative max. If your derivative changes from negative to positive, then you're dealing with a relative min. Okay, let's apply that idea to the following example. I've got before me a basic function that I know about. I know that this is a parabola opening up, and I know, because I know the shape, I know that it has one extrema point. Alright, so we have to first of all find our critical points, okay, which is where the derivative is 0 or undefined. So we've got a derivative as follows. The critical point is when the derivative is 0 or undefined. Well, this derivative will only equal 0. The derivative will never be undefined. So therefore, at x equals 1. This is my critical point. This is a point where the derivative is 0 and where a relative min might occur. So to decide if this critical point actually is a relative min, I'm going to apply the first derivative test, which means I am going to look on either side of x equals 1 to see whether the first derivative changes sign. So I'm going to look at the sign of the first derivative. I'm going to look at the effect of that on the original function. And let's take a number less than 1 and plug it into the derivative. So if I take x equals 0, for example, I get a negative first derivative. If I take a number more than 1, like 2, I get a positive first derivative, which means that my original graph was decreasing and then increasing. Okay? I have a change in the sign of the first derivative, okay, from negative to positive, which tells me that x equals 1 is the location of a relative minimum, and I always have to explain why, because the first derivative changed from negative to positive. Okay. Now the question was also, what is the value of the relative minimum? And by that I mean the y value. So the relative min value is f of 1. And if I plug 1 into my original function, I get 3. Okay? So in other words, this graph has a minimum value of 3 when x is equal to 1. So what you've basically just calculated here is the vertex of the parabola. There's a second way that we can determine whether a critical point is a relative min or max as well. This method only works, however, if you're dealing with a function that has defined first and second derivatives. So you can't have a critical point where the first derivative is undefined, which is generally a cusp, because if the first derivative doesn't exist, the second derivative can't exist. So this method requires that the first and second derivatives exist. And this is how the argument goes. If you have a critical point, derivative equaling 0, and you are on a concave down part of the graph, then your critical point must be a relative max. If you have a critical point, derivative equaling 0, on a concave up part of the graph, then your critical point must be the location of a relative min. This is what we call the second derivative test. If you have a location where the derivative is 0, and at that point you are on a concave up part of the graph, which means that the second derivative at that point is positive, then your location x equals a must be the location of a relative min. If your first derivative is 0 and you're on a concave down part of the graph, which means the second derivative at a is negative, then x equals a must be the location of a relative max. Okay, so let's do the same question that we did previously, but this time using the second derivative test. We want to find the location and the value of all relative extremas. Alright, so first of all we need, once again, the critical points. So you have critical points at f prime equaling 0. And so our critical point is x equals 1. Now we want to determine whether this critical point is the location of a relative min or max. So we have to first of all indicate that the first derivative at 1 is 0, which we know it is because we've just solved for that. Now we need to look at the second derivative. Now the second derivative is 2. Now the second derivative, therefore, at my critical point is also 2. And so since my second derivative is positive, since the first derivative was 0, and the second derivative at 1 was positive, therefore x equals 1 by the second derivative test is, right there, is the location of a relative min. And the value of the relative min is f of 1, which we previously calculated to be positive 3.